When you start, these small alkalis like methanol. Methanol is a liquid. It's a very volatile liquid, so it easily evaporates. Um, and then ethanol is a liquid. Isopropyl alcohol is a liquid. But when you get to these very large alcohols, then they become solids. And then things like methane. A lot of this is just memorization. Methane's a gas, ethane's a gas, propane's a gas, but butane is a liquid, and then pentane's a liquid, hexane's a liquid, and then eventually you reach the point where they become solids.
Yeah, I thought the only thing you could consider liquid was water. I must have missed that.
Alcohols, a lot of alcohols are liquids, but some alcohols are solids too.
Okay.
But they have a pretty low boiling point, so they're easy to vaporize. Yeah, that's going to be given, especially complex alcohol.
Yeah, like C6H5COSH. That
C6H5
COSH.
SH.
It's so funny, they started off with it as a liquid and then they turned it into a solid, so it might have been their error when they were writing the...
Yeah, you wouldn't need to know. For example, C6H5COOH is actually a solid. This is called benzoic acid. This is the thio version of benzoic acid. Thio just means to replace one of the oxygens with sulfur. That's what we do here. How do you know it's a solid? Depends on how it packs and other things. So there are certain clues that might give it away to you, but you would have to know much more about structure to do that. It's like saturated fats versus unsaturated fats. Saturated fats are typically solids. Unsaturated fats are typically liquids. And you can see that from the structure, but you would have been told some additional information. You'd see it here.
Yeah.
Saturated fats have this long zigzag chain of carbon atoms. There are no double bonds here. If you put a double bond, it ends up kinking the structure. So when you pack these together, they pack nicely. And since they pack nicely, then you can maximize the intermolecular attractions. In this case, van der Waals, this like what we call dispersion type forces here. Whereas here, this is kink, and so they don't pack so nicely. So these turn out to be liquid fats, and these turn out to be solid fats. And there are little clues like that, but you would have to know a little bit of information beforehand, so I wouldn't worry about it too much at all.
Now, for certain things, sometimes it could be a gas or a liquid.
Yeah.
When you're having combustion, and how would you know that? Just
What do you mean?
like I think you had just said butane was a liquid, or I forget which.
That's memorization.
Okay.
It's looking for a pattern. This is one of the things you do initially when you look at alkanes. Let's see. Let's go to physical properties of alkanes. Maybe it has it here. So we don't memorize like everything. We just memorize certain patterns if it's possible. So one of the patterns is this. Like for example, methane. Methane's boiling point is minus 164, so that's a gas. Or ethane, minus 89 is boiling point, because that's a gas. Propane is a gas. Butane, the boiling point is minus 1. Minus 1 means at 25 degrees C it should be a gas. Usually when you have a butane lighter, though, it's a liquid. It's a liquid because they usually store it under a little bit higher pressure. And so oftentimes butane, we'll see in the lighter as a liquid. And so this would be either gas or liquid. It's getting close. But definitely pentane's boiling point is going to be above room temperature, but it's very volatile. Pentane boils at 36 degrees Celsius. So this is going to be a liquid. Hexane's a liquid. Octane's a liquid. Decane. Decane is a liquid. And then this table goes on. So eventually what we'll see is we'll see that the melting point is going to go above 25. When the melting point goes above 25, then these turn into a solid. So can you see the trend here? And the trend here? So it's going to be less and less liquid, more and more solid as we go along. Here's the trend line here. It's not linear quite, but you can see it depending on the number of carbon atoms, how the boiling point changes.
That's the same with like oil when they're manufacturing oil. Like the bottom of it is more like a solid, but as they burn it, it becomes a gas.
Yeah, as the temperature goes up. This is just showing solids, not solid, gases. Gases will have a boiling point below room temperature. Liquids have a boiling point above room temperature. And then we look at the melting point to get what the solids are. So about 4 or 5 carbons, it transitions from a gas to a liquid. And so above 5 carbons, we're going to be liquid for sure. And 4 carbons, because butane, typically liquid. And so these patterns you would memorize in organic chemistry. Organic chemistry, you'll typically get questions like that, where you'd have to predict it. But again, that's a bit of memorization there.
I was wondering if you're able to do for chapter 5 homework, number 77.
Number 77, chapter 5. 77B? C? Yeah. You can do that. Um, 77C, okay, AS2S3. Arsenic is a semi-metal. It lies along this line here. And since arsenic is a semi-metal, we could use either the nomenclature rules for ionic compounds, or metal and non-metal, or the nomenclature rules for non-metal.
Semi-metals are metalloids, right?
Yeah, semi-metals are metalloids. And so there are 2 ways of naming it. AS2S3. First is if we treat that as a non-metal. And so if we treat it as non-metal, then it would be diarsenic, trisulfide. The other name for this would be what? Well, the other name for this is if we treat that as a metal. If we treat it as a metal, what's the charge on arsenic? Yeah, the charge on arsenic would be 3+. So this could also be called arsenic, Roman numeral 3, sulfide. these are two, and both of these names are used commonly for this. So if we take arsenic 3-sulfide, and then react it with what?
Nitrate.
Nitrate. So As2S3 plus nitrate produces, what's that called? H3ASO4.
Arsenic acid.
Arsenic acid. Arsenate is ASO4 3 minus, and so this is arsenic acid. Arsenic is right below phosphorus in the periodic table. And so phosphoric acid is H3PO4, arsenic acid is H3ASO4, arsenate 3 minus, plus sulfur plus nitrogen monoxide or nitric oxide. So the first thing is we split it up into two half reactions. In the first half reaction, As2S3 goes to what?
Arsenic acid.
Arsenic acid. Okay, that's where the arsenic goes, but where did the sulfur go?
Sulfur.
Yeah. And so this has got to go to two things. It's got to go to arsenic acid plus sulfur, otherwise we're missing the sulfur. The other half reaction is nitrate must go to nitric oxide. So, doing this, we balance the first one. Was the problem splitting this?
Yeah, it's
Yeah.
confusing.
Yeah, so now we just balance it as usual. We'll just start off with arsenic. We have two arsenics here. We have one arsenic here. So how can we balance out the arsenics?
You can double the arsenic acid.
Yeah, we just double the arsenic acid here. Okay, now it's balanced. And then over here we have 3 sulfurs. Over here we only have 1 sulfur. So how can we balance out the sulfurs?
Triple the sulfur.
Yeah, we'll just triple the sulfur. And then we balance out the oxygens. So we have 4 oxygens on the right and none on the left. So that means we have 4 H2Os. And then balance out the hydrogens. We have 8 hydrogens on the left, 0 hydrogens on the right. And so we just add H plus, H plus.
We do have hydrogens in the right, don't we? In the H2.
Oh yeah, you're right. There's 6 of them here. I don't need 8. Just need 2. But 6 plus 2 will give me 8. And so this is not 0. This is 6 hydrogens. Does that look right?
Don't we have 8 oxygens on the right side?
Oh yeah, we have 8 oxygens. I forgot the doubling. 8 oxygens. So that's going to give us 8 waters, which is going to give us 16 hydrogens. All right. So I have 6 here. That means I have to add 10 H plus. That's good. You caught it. The other place you would catch errors is here. We go As2S3 plus 8 H2O goes to 2 H3ASO4 plus 3 sulfurs plus 10 H plus. How we would catch it is we just check if it's balanced. So 2 arsenics, 2 times 1 is 2 arsenics, 3 sulfurs, 16 hydrogens. This is 6 plus 10, 16 hydrogens, 8 oxygens, 8 oxygens. So the atoms are balanced. Then we check for charge balance. When I check for charge balance, this is 0 and 0, but This is plus 10. The charges aren't balanced because I forgot a step. What step did I forget?
The electrons.
The electrons. I forgot to balance out the charge. And so, fortunately, there's another error check here when you check the balance. And so, on the left it's going to be 0 charge. On the right we're going to have plus 10. And so I have to add 10 electrons to the right. And so I'm just going to tack on 10 electrons here at the end. Okay, now the charges are balanced. And so the atoms are balanced, the charges are balanced, and this is the balanced half reaction there. Have you seen nitrate goes to NO before?
Yeah.
And so some familiarity with this chart is good. Because when I look at this chart here, I see nitrate plus 4H plus 3 electrons goes to NO plus 2H2O. So I don't have to do this one. This one I'm just going to copy off the chart. Nitrate plus 4H plus 3 electrons goes to NO plus 2H2O liquids. And so this is the other balanced half reaction. So in this reaction here, I'm losing 10, and in this reaction I'm gaining 3. So probably the easiest thing to do is cross multiply these. So the second one I'm going to multiply by 10 times. The first one I'm going to multiply by 3 times. And that way I can get the electrons to balance. Do that here. So I'm going to have 3As2S3 plus 24H2O plus 10 nitrates plus 40H plus 30 electrons. This is going to go to 6 arsenic acids plus 9 sulfurs plus 30 H plus 30 electrons plus NO plus 2 H2O. Here. Okay, then try to simplify this. I have 2 waters here on the right. I'm going to cancel 2 out of the 24. That's going to leave me with 22 waters there. I have 40 H pluses and 30 H pluses, so I'm going to cancel out the 30, and that's going to leave me with 10 H pluses on the left. The 30 electrons will cancel out. There's supposed to be 30 electrons here. Electrons cancel out.
Shouldn't it be 10 nitric oxides?
Oh yeah. Should be 10 nitric oxides. Let's fix that. Okay, anything else cancel out?
It also be a 20 H2O.
What's that?
Shouldn't it be a 20 H2O at the very bottom?
20, you're right.
Gotcha.
2 times 10, it should be 20 H2Os. It's 20 H2Os, which is going to make this 4 H2Os at the end. Okay, anything else? I think that's all right. So we'll go 3As2S3 plus 4 H2O plus 10 nitrates plus 10 H plus. This is going to produce 6 H3 ASO4 plus 9 sulfurs plus 10 NO. Yeah. All right, so let's see if it's still balanced. So I have 6 arsenics here, and I'm going to have 6 arsenics here. And then 3 times 3 is 9 sulfurs, 8 hydrogens. Oh, 8 plus 10, 18 hydrogens. So 6 times 3 is 18. 4 plus 30, 34 oxygens. So 6 times 4 is 24 plus 10 is 34 oxygens. 10 nitrogens, and that's it. So the atoms are balanced. Then let's check the charge. So this is 0, 0, minus 10 plus 10, 0. This is 0, 0, 0. So the charges are balanced. And so this would be it. Now, did they say this was an acidic solution or basic solution? Acidic solution? And we're done. If this were in basic solution, we'd do one more step. We'd have to get rid of these 10 H pluses. So if this were in basic solution, I'd add 10 hydroxides to the left, that converts these into water, and then 10 hydroxides on the right, which would just be added on the end. The final thing we do is we look at the driving force. And so we get an idea of the strength of the oxidizers and the strength of the reducers. So over here, the AS2S3 in the water, that's acting as what, the reducing agent or the oxidizing agent? Reducing agents gain or lose electrons. Like metals are good reducing agents. Do metals gain or lose electrons? Lose. And so this is losing electrons, 10 electrons. And so this is a reducing agent. If that's the reducing agent, then this will be our conjugate oxidizing agent. And then over here, this is our oxidizing agent, and this will be our conjugate reducing agent. And so we have this as our reducing agent here. And then over here we have this as our oxidizing agent in the forward direction. In the reverse direction, the arsenic acid and the sulfur will act as our oxidizing agent, and the NO gas will act as our reducing agent. And there's no water here. This is NO plus water, but we don't have water. It's just because the net reaction doesn't require it for this particular combination. Because this reaction occurs, that is, they got product here, we know we're already going from stronger to weaker here. And so that means that nitric acid is stronger oxidizer than arsenic acid and sulfur. And the arsenic 3 sulfide is a stronger reducer than the nitric oxide. Okay, other questions? Well, since I did this skeleton redox, this is from the homework. Chapter 5. We can take a look at all these are skeleton redox. You see they're given the products. We could also take a look at the chart method. So we use the chart method a little bit here in this problem because we just grab this half reaction off the chart. But the chart method is not gonna give us the product, so all these are giving us the product.
I have a question.
Mm-hmm.
Are we going to be provided with a table in the exam?
Yes.
Thank you.
Yeah, you don't have to memorize anything. Okay. So again, this is an example of a skeleton redox over here, where you're given the product. When we use the chart method for redox, I guess I'll talk about it right now. We don't necessarily know what the products are. We're just trying to figure out what some reasonable products would be. So for example, if we take copper metal and nitric acid, will copper metal and nitric acid be good single replacement reaction? The answer is no. Why is this not a good single replacement reaction?
Isn't hydrogen more reactive than copper?
The hydrogen?
Yes, therefore it would prefer to stay with
Nitrate?
rather than copper.
Nitric acid is a strong acid, so the hydrogen breaks off easily.
It goes from less active to more active. Because I feel like we did one like this yesterday.
What's that? I mean,
Just go from being less active to more active.
yeah, that's what we try to do here. We did something like this yesterday. We got no reaction. Do we expect no reaction here again? Yesterday we ended up with copper solid plus 2H plus, or actually it was HCl, yielded NR. Because we're going from less active copper to more active H2 gas. Remember that from yesterday? So this is the same type of deal, right? It's copper, but rather than hydrochloric acid, we're using nitric acid. So do we treat these the same? Can you tell? If you can't tell, then use the chart method instead of single replacement. If you use single replacement here, A plus Bx yields AX, which would be copper 2 nitrate. We'd like to take copper all the way to copper 2 and hydrogen gas. Then we compare. Copper is a weaker reducing agent. Hydrogen is a stronger reducing agent. So the driving force is backwards here, and so we expect no reaction here. Correct?
Mm-hmm.
This turns out to be wrong. There is a reaction. Yeah. No reaction is wrong. There's a reaction. And you could have figured it out because why? I mean, how could you have figured out that there's going to be a reaction here?
Because nitrate is too strong, it's not gonna be a spectator.
Yeah. Right. Nitrate's too strong in the presence of
H+.
H plus. So we have H plus here, and we have nitrate. And so when we have the combination of nitrate with H plus, then it's a powerful oxidizer. Nitrate in the combination of H plus is a powerful oxidizer. So it's not going to want to spectate. It's going to want to participate because nitrate in H plus is a stronger oxidizer than H plus. Down here. In single replacement, it's just the H plus that's reacting. And so, if you didn't recognize this as an oxidizing acid, this is an oxidizing acid. Oxidizing acids don't work in single replacement. And so, for something like this, we have to use the chart method. And then using the chart method is we're just going to go to, see what copper, actually what else is present? Copper, H plus, nitrate, and water. See what each of these species can do. So copper can only do one thing, it's a reducer. It's on the right side. H plus is on the left side, so that's an oxidizer. But we also have nitrate, but nitrate needs H plus as well. So this is an oxidizer. And then we have water, which is both an oxidizer and reducer. And it turns out the strongest oxidizer is going to be nitrate and H plus. And the strongest reducer is going to be copper. And so this metal, at least, is a better reducer than water. So what we do is we just copy it off the chart. Nitrate and H plus, we'll need 4 H pluses, plus 3 electrons is going to go to NO gas plus 2 waters. And that's a common half reaction for nitrate going to nitric oxide. And then copper, we'll reverse that reaction up there. Copper solid goes to copper 2 plus 2 electrons. Okay, from here it's similar to the other problems. That is, what I'll do is I'm just going to cross multiply these. And so I'll have 2 of these and 3 of these. Which will give me 6 electrons. And so we're going to end up with 2 nitrates plus 8 H plus 6 electrons plus 3 coppers. It's going to produce 2 NO plus 4 H2O plus 3 Cu2 plus 6 electrons. Now most important is the electrons must cancel, just like in skeleton redox. And then we try to simplify whatever else can be simplified here. Looks like nothing else. And then we'll just write the simplified equation up here. So we're going to have 2 nitrates plus 8H plus 3 coppers is going to produce 2 NO plus 4 H2O plus 3 Cu2 plus. Okay, oftentimes, well, actually, before I do much more, I probably should have checked to see if there's driving force. Because if there's no reaction here, there's no reason in simplifying it. And so to check for driving forces, I need to label the species. Probably the easiest place to label a species are from the half reactions here. So this is the oxidizer, gaining electrons, and this must be the conjugate reducer. This is our reducer, and therefore this must be our conjugate oxidizer. And so we're comparing these, nitrate and H plus versus Cu2 plus. This is the oxidizer. So nitrate and H plus versus Cu2 plus. Here's Cu2 plus. Here, the nitrate and H plus is there. So this is going from stronger oxidizer to weaker oxidizer. And so we do have driving force. That means the reducers must hold true because of the conjugate relationship. So copper must be a stronger reducer than nitric oxide in water. This must be a weaker reducer. So copper must be a stronger reducer than nitric oxide in water, which is true. So we have driving force. The driving force is going from stronger to weaker. And so there is a reaction there. So some problems we have to use the chart method. There's no other way. Some problems we might be able to get away with a single replacement. But it's just another thing. Here we had to predict the products. In skeleton redox we didn't have to predict the products, so it's a big difference there. Here we don't know if there's a driving force. In skeleton redox there must be a driving force. Otherwise they wouldn't have formed those products. Other questions? No? Well, where did I leave off last time? Chapter 4? Were we looking at some problems from chapter 4 earlier? I think, yeah. The chapter 4 problems is just to get familiar with, or more familiar with chemical reactions, just a little bit more exposure to chemical reactions.
We haven't seen sublimation yet, have we?
Sublimation? No,
Yeah.
not yet. Sublimation comes in chapter 14. Chapter 14. Does anybody know where we left off?
I know we're past 47 at least.
Past 47?
I think the last one we did was 51.
51?
Maybe 70?
Number 70? All right, thanks. Yeah, did I talk about hypochlorite, bleach? Yeah. Interesting thing, you know, when we think about these properties, you know, for some reactions it makes a world of difference. You know, for other reactions it doesn't make any difference at all. And so what I'm talking about is something like this. Normal bleach is sodium hypochlorite, NaOCl. That's bleach, aqueous. Bleach is a pretty good oxidizer. You know, or NaClO. That's another way of writing it. What are the oxidation states? Na is +1. And then what goes next? Chlorine or oxygen? Usually the rule goes the more electronegative gets its preferred charge. And so if there's a struggle between chlorine and oxygen, who would win?
Oxygen.
oxygen. Oxygen's smaller, even though in some books chlorine and oxygen have the same electronegativity, 3.5 for oxygen, 3.5 for chlorine. They aren't the same. Chlorine's a much bigger atom. And so oxygen wins, and it's going to get what?
Minus 2.
-2. And that leaves chlorine as
Plus 1.
+1. And so these are two different ways of writing the formula for bleach. NaOCl or NaClO. Will HClO, this is called hypochlorous acid, have a bleaching action? Bleach, in other words, bleach is an oxidizer. Oxidizers are electron poor or electron rich.
Electron poor.
And when you look at it, who's electron poor? Are sodium ions electron poor?
No.
No. Not oxygen. Chlorine?
Yeah.
Yeah, chlorine is in. And so sodium hypochlorite, hypochlorous acid. Sodium hypochlorite and hypochlorous acid are going to have the same redox properties, but they're going to have different acid-base properties. So for example, sodium hypochlorite is a weak base. That is, the OCl minus is a base. Sodium ions are neutral. And this is acid. And so sodium hypochlorite is a base, hypochlorous acid is an acid. So their acid-base properties are on opposite sides in terms of reactivity. But in terms of redox, they're the same. You see, these two things are going to be the same in terms of redox because of the hypochlorite ion. It's electron poor. And the same thing with calcium hypochlorite. Calcium hypochlorite is going to be like bleach. It's got hypochlorite. Okay. It's a base. So in this case, we made HCl. Do you know, we didn't make HCl, we made chlorine gas. Do you recall how we made chlorine gas yesterday? You got some solid potassium permanganate, and when you take potassium permanganate and mix it with water, it makes a purple solution that looks like grape juice. And then you mix it with some HCl. And eventually what's going to happen is the purple color, this is what should have happened. I don't know if this is what happened in your observations, but the purple color should have disappeared and be replaced with a very, very, very light pink color or colorless solution at the end. And what happens there is that the permanganate gets converted into manganese 2. Manganese 2 is very light pink. And the chloride in HCl gets converted to chlorine gas. Well, we don't have to use potassium permanganate as the oxidizer. We can use bleach as the oxidizer. And so we take bleach and mix it with HCl. The bleach is going to oxidize the chloride to chlorine in this case. And we form chlorine gas. So that's a reaction in summary. Okay, next. Looking at 77. The reaction of 15.0 grams of C4H9OH. What do you suspect that is? C4H9OH. Well, what organic functional group does that look like?
It's
hydrocarbon with an OH bond is called a, looks like it has one of these. Those are called
Alcohol,
alcohols. And how many carbons do we have?
4,
4 carbons. 4 carbon alcohol. What's a 4 carbon alcohol?
you know.
Butanol. This is looking like butanol. But the problem with this formula is we don't know which butanol we're looking at. Is it 1 butanol? Or 2 butanol? So in other words, is the alcohol in carbon 1, or do we move the alcohol to carbon 2? Because if we move it to carbon 2, then we'll move this hydrogen over there. And so is it 1 butanol or 2 butanol? We don't know. Those are isomers of this. Could it be 3 butanol? Well, there's no such thing as 3 butanol, because 3 butanol would be the same as 2 butanol if we count from this end. Is it 4 butanol? No, 4 butanol would be the same as 1 butanol if we just reverse the counting order. And so this is either 1 butanol or 2 butanol. So we're going to take butanol, sodium bromide, and sulfuric acid, and we're going to make this C4H9Br. And the reaction shown. Let's take a look at the reaction. Shown here. Here it is. What kind of reaction is that? If we look at this, what kind of reaction is that? You think it's a redox reaction?
It looks like a metathesis.
Metathesis? Kind of looks like a metathesis, but if it were metathesis, then it's, yeah. Kinda. This hydroxyl group, they call it, the OH is not an anion. It's not hydroxide, it's an alcohol. But sometimes in metathesis, we can take molecular compounds and pretend as if they're ionic. You know, I used to do this with the alkali metals. The alkali metals are powerful reducing agents. These are like sodium. Sodium is a powerful reducing agent. It's a very powerful reducing agent. We have to watch out because sodium is powerful enough to reduce water. In other words, water is a strong enough oxidizer to oxidize sodium. So sometimes when molecular compounds, we treat it as ionic in a way. And so we have an A plus BX pattern. In this case, B is hydrogen, X is hydroxide. And so we're going to treat those as ions. And so we're going to form AX plus B. A would be sodium, X is hydroxide, so we'll form sodium hydroxide, plus B. B is hydrogen, so hydrogen likes to pair up, and so we'll just have H2 gas. So sometimes we do that, and so sometimes we might imagine this as a hydroxide. And in terms of metathesis, we should form sodium, what? Sodium hydroxide and butyl bromide. Yeah. And so we should have probably formed sodium hydroxide. If this is not ionic, but sometimes we can kind of treat it like this, like we did here for water. But do you see any sodium hydroxide there? I see butyl bromide here, so we lost this OH. Replaced it with a Br, but where did the OH go? Well, maybe the OH attacked H2SO4. Just one of the OHs attacked it to make HSO4 minus. So this could be a combination of metathesis, if you want to call it like that, and acid base, maybe. But it's not really metathesis as written in that sense, in a perfect sense. The other way of looking at this is a redox reaction. Did any of the oxidation states change? So we look at the C4H9OH versus C4H9Br, sodium times bromide, H2SO4. Do you see any oxidation states changing? No. No oxidation. This is not redox. And so if it's not metathesis, it's not Bronsted acid base, then it's got to be what? Lewis acid base. Sometimes we'll have a combination of reactions, though, as well. And so this might be considered, if you want to do a pseudo double replacement, normally we don't call this AX, or BX, or whatever. Actually, this would be AB. This is double replacement, AB. And then sodium bromide, this would be our CD. So this is kind of a metathesis reaction here. And so in this kind of metathesis reaction here, I'm going to call this C4H9. C4H9. We have 4 carbons, 2, 4, 6, 8, 9 hydrogens, C4H9. Bromide. This is not an ionic compound, though, because this is going to be C covalently bonded to bromine. So it's not ionically bound. And the other product of this would be sodium hydroxide. That's step 1. In step 2 is kind of a weird reaction. In step 2, we would have sodium hydroxide plus sulfuric acid. Now, this is always complicated because since it's always complicated, we pick one way of doing it and stick with it, but sometimes it's done differently. So normally when I do this here, in double replacement or metathesis, we do complete reaction. We assume complete reaction. It may not always be the case. We might not have complete reaction. It's like, when we do combustion, we always assume complete combustion, but it's not always the case that we'll have complete combustion. Sometimes we just have partial combustion. Doesn't quite work out. So if we did complete reaction, then how many sodium hydroxides do we need to neutralize H2SO4? H2SO4 is what we call diprotic acid. And so how many sodium hydroxides do you need to neutralize H2SO4? Actually, we need 2. Each hydroxide, we need 2 of those. And what we're going to form is sodium sulfate and 2 waters. And so in this case, we're going to neutralize both hydrogens here. But it doesn't mean that partial reaction is not possible. We could have partial reaction. That is, let's say I didn't have 2 sodium hydroxides. Let's say I only had 1 sodium hydroxide. If I only had 1 sodium hydroxide, I'm not going to neutralize both hydrogens. In fact, I'll only neutralize one of the 2 hydrogens. If I only neutralize 1 out of the 2, then the second one stays on there. If the second one stays on there, then what I'm going to form is I'm going to form sodium hydrogen sulfate or sodium bisulfate and water. So this would be what we call step 1 of neutralizing a diprotic acid. Step 2 would be I'd need more sodium hydroxide, but if I ran out, let's say you ran out of sodium hydroxide, then you can't neutralize that second hydrogen. So if we ran out of sodium hydroxide, it's going to stop here and form sodium bisulfate and water. So this is kind of a combination. of reactions. But this metathesis is not really metathesis. This is more Lewis acid base reaction here. Let me talk about Lewis acid base a little bit more, but before I do that, I want to talk about how we handle acid base reactions in general. Okay. For acid-base reactions, we have a set of acid-base reactions that are also metathesis reactions. So an example of this is, let's look at ammonia plus acetic acid. Ammonia plus acetic acid. Acetic acid can be written in two ways. We could write it CH3COOH as well. Was that the right one? Maybe I wanted to do sulfuric acid. Let's see. Well, I'll do this one right now. There are two ways of handling some of these. If we can put it in metathesis format, we do that. And so metathesis, this could work if this is aqueous ammonia. The aqueous ammonia reacts with water to form a little bit of ammonium hydroxide. And so this will be our AB. Our AB will be ammonium hydroxide that's formed from ammonia and water. And then our CD will be just acetic acid here. And so we have ammonium hydroxide plus acetic acid will give us ammonium acetate and water. Okay, let's look at the driving force for this. In acid-base reactions, we want to look at if we're going from a stronger acid to a weaker acid. Are we going from a stronger acid to weaker acid?
Yes.
Yeah, and what's a weaker acid?
H2O.
Is H2O the weaker acid? So we go from stronger acid to weaker acid, and the weaker acid is H2O. Yeah. But something's going to happen. Okay, so we have driving force here, so let's simplify this equation. If we simplify this equation, what can we cancel anything out?
So we have a water.
Looks like I have one water here and one water here. I'll cancel that out. Did I just cancel out my driving force? If I just cancel out my driving force, there's no driving force for this reaction. Is that correct?
The driving force would be any strong base to weak base still.
The weak base being what?
Ammonium acetate.
Ammonium acetate, yeah. All right, so let's hold this for a second. The other way of doing this reaction is via the Bronsted. in the Bronsted is the chart method. And the chart method is, the first thing is we inventory everything in solution. So we have ammonia, we have acetic acid, and we have water. Ammonia is a base. Sometimes it can act as an acid. It's a very poor acid. Acetic acid is an acid. Water is both an acid and a base. The strongest acid is going to be acetic acid, and the strongest base will be ammonia. And so in Bronsted, what we do is we transfer a proton from the acid to the base. So all we do is we transfer one proton at a time. So in the previous example, with H2SO4, we would have just transferred one proton at a time for that. And so what does this form? This is going to form ammonium and acetate, or ammonium acetate. Ammonium acetate is a soluble salt, so it's going to dissociate like this. And then we look for driving force here. Okay, ammonia is our base, acetic acid is our acid. Then we go backwards. If we go backwards, who loses the proton, who gains the proton?
Ammonium loses the proton.
Yeah, and so this is the acid going backwards, and acetate gains the proton, making it the base going backwards. And then we compare the acid strengths. Which one's a stronger acid, acetic acid or ammonium? And there we just go to the acid-base chart here. And compare acetic acid, CH3COOH, this is acetic acid, versus ammonium ions. I don't see it yet. Here's ammonium ion. So which one's a stronger acid, acetic acid or ammonium? Acetic acid. So in this case, we are going from a stronger acid, acetic acid, to weaker acid, ammonium. And so in this case, it wasn't really the water that was the weaker acid. What was the weaker acid? Over here. The weaker acid was the ammonium here, not the water. And so the weaker acid is ammonium ion. And that's what's going to lose protons going backwards to form ammonia. You have to be careful because, you know, in Chem 4, you might have learned that the driving force for double replacement reactions is the formation of water. You know, it's not always the formation of water, because if we did this as double replacement metathesis reaction and we did form water, the water just disappeared. So that isn't the case here. All right, so that was now. You know, metathesis involves ions, and it's ion combination. Sometimes we can kind of, you know, take a molecular compound and make it look like an ionic compound, like water. Water is not an ionic compound, but in single replacement, sometimes we'll write water as HOH, you know, C. It happens. And so we'd have like very powerful reducers, sodium, lithium, etc., react with water. And so this would be our A plus BX. But other times what we'll do is we'll just do Lewis acid base reactions.
So hydrogen behaves like a metal or a gas?
In this case?
Well, just like us. Would that determine if it's like an acid or a base, if it behaves like a metal or a gas? If that makes sense. Because, you know, on the periodic table, it's in group 1, but also it's over in 17.
Yeah. Yeah. Right. Now I get it. Hydrogen behaves like an alkali metal or a halogen.
Halogen, yeah. So would that determine if it would be more on the acid side or the basic side?
The hydrogen is not a very good, that hydrogen there is the element hydrogen. And so hydrogen can be a reducing agent and lose 2. Like that. Or hydrogen can be an oxidizing agent and gain 2 electrons to form 2 hydrides. And so what dictates its redox properties, would be on which side it lies. Because over on the right side, you have the oxidizers, the reducers, on the right side of the periodic table. On the right side, all these, not the furthest right, because the furthest right, these are fairly unreactive. These are not good oxidizers and not good reducers, the noble gases. But starting with fluorine, fluorine wants to do what? Is fluorine an oxidizer?
Yeah, that's what I was trying to get at, is like if hydrogen, there would be an oxidizer
Yeah.
compared to if it's an alkali, it's a reducer.
Yeah.
Sir, yeah.
Yeah. But whether it acts as a reducer or oxidizer just depends on what you mix it with.
Okay.
So in order to oxidize hydrogen, you just need a more powerful oxidizer than H+. In order to reduce hydrogen, you just need a more powerful reducer than hydride. But hydride's not on the chart, but we figure out what are more powerful reducers. And so it just depends on what you react it with. It's like water. Water can act either as an acid or a base, so which one is it? Well, it depends on what you react it with, because if there's nothing to react it, then it just acts neutral. It depends on what you put in to the beaker. That's going to depend on whether it's going to act as an acid or base. Is water going to act as an oxidizer or reducer? Well, it depends on what you put in, mix it in with. And so how it behaves depends on what you're trying to react it with. But it's all of those, there. There are some things you can memorize, though. Like non-metal oxide. You might have had to memorize this in Chem 4. I didn't make my students memorize it, but non-metal oxides versus metal oxides. Do you know non-metal oxides are Lewis acids? And so you might have had to memorize this. This is one of the 9 types of reactions that you're supposed to memorize in Chem 4. Non-metal oxide plus water. Non-metal oxide plus water yields what? Anybody know? Probably. And so this is an example of a Lewis acid-base reaction. It leads to acid. Metal oxide plus water leads to base. I didn't have anybody memorize it in my class. But this is Lewis acid-base reactions. CO2 is actually both a Lewis acid and a Lewis base. So what we do here is we analyze the structure of this, the Lewis structure. And we analyze it, we look for formal charge. Are there any formal charges on CO2? No, there are no formal charges. If there are no formal charges, then when we look at partial charges, are there partial charges? Yes. Like oxygen's delta minus, because it's more electronegative than carbon, and that's going to make carbon delta plus. So when we have an oxygen, It's delta minus that has a lone pair. That's what we call a base site, a Lewis base site. When we have an atom that has a partial positive charge that might be able to accept a lone pair, this is called an acid site. Now we're going to react this with water. Water also has an acid site and a base site. What's the acid site in water? Yeah. What's the base site? Yeah, oxygen. So we can do the same thing here. This is the acid. The base. Now,
So when it comes to, going back to water, when it comes to oxidizers and reducers, oxidizers like to take electrons, right?
yes.
Okay, so, just to put this in like, real world terms, I was reading somewhere that, you shouldn't drink distilled water because it could have negative health effects. And is that because the distilled water behaves like an oxidizer?
No.
No? Okay.
There's certain things, there's a certain balance that you have for electrolytes,
Uh-huh.
and you can have certain processes occur. So, one of those is this. Lysis. Have you heard of lysis? Lysis. Lysis is like hydrolysis. You remember what was hydrolysis? Hydrolysis is had to do something to do with water. Hydrolysis. Bases do what? Bases hydrolyze water to form hydroxide. Acids hydrolyze water to form hydronium. Now, hydrolyze is we're breaking apart the water. Well, lysis typically is known for breaking down the membrane of the cell. And this is something we're going to get into. You'd asked me about you asked me about something that's going to be in chapter 13, chapter 12.
You mean sublimation?
Sublimation, yeah.
Solid to gas?
Right. There's going to be another thing that's going to come later. And that's osmosis. Osmosis is we need an electrolyte balance. Electrolytes are important, or things that are dissolved in here. It doesn't have to be electrolytes. It just could be dissolved species in here. And if this is, there's a difference in concentration. So let's say the concentration here, so these square brackets mean the concentration, versus the concentration outside here. Let's say the concentration outside is much lower than the concentration inside. There's an imbalance in concentration. So this high concentration solution here is at a different energy than the low concentration solution here. It's imbalanced. So what happens is the two levels want to equalize. And so what we're going to have is we're going to have net migration of water in here into the cell. Let's say this is a cell membrane here. So what happens is the water keeps migrating into the cell membrane. Eventually the cell membrane can burst. You know, it's like a balloon. You keep blowing up the balloon in the direction. So that type of thing can happen.
So it's not because it's a oxidizer or reducer, it's just,
No.
okay,
It's just because of what we call osmosis.
yeah.
All right, well, what was I doing now here? And how water reacts depends on what you react it with. And so water can go either way, it can be an acid or a base. Same thing with CO2. CO2 can go either way, it can be an acid or a base. Let's make CO2 the base. Now, in Lewis, acid-base theory, what do bases do? Bases are what? Or how about acids? Acids, a Lewis acid does what? Accepts what? Electron pair acceptor. So acids are electron pair acceptors. Bases are electron pair donor. So in Lewis, we follow the electron pair. And so we have two choices here. I'll label it choice A. I'll label this choice 1, 2. So do you see I have a base site here? I have negative charge density and a lone pair. So what I'm going to do is I'm going to have this lone pair be donated to this hydrogen here. Does that hydrogen want another pair of electrons? How many electrons does it take to fill the valence shell of hydrogen? Only 2. Hydrogen wants a duet, so this is too many electrons. Do you see that's going to be too many electrons? We can't have it. It's too many electrons. So either it's going to revert back to what it was before, or it's going to kick these electrons out. So I'm going to call this 1. This lone pair goes here, attacks that hydrogen. In other words, this base is going to pluck that hydrogen off as a proton and leave the electrons behind, like this. It's 1, 2. And so here, water is acting as the acid. So this is 1, 2. What's the other possibility? The other possibility is if water acts as the base. So if water acts as the base, then this lone pair here is going to get pushed into this carbon. This lone pair, you know, look at the charge. This is negative, this is positive. There's going to be electrical attraction there. But there's going to be a problem. If that lone pair gets pushed into the carbon, does carbon want another pair of electrons? It doesn't want another pair of electrons because it already has an octet. Can carbon have more than an octet? No. Carbon can not have more than an octet. And so that's going to be too many electrons. But you know what can happen? What can happen is if this pair of electrons comes into carbon, what carbon can do is kick this pair off and give it to oxygen. Okay, this is, I'm going to call this AB rather than 1, 2. So the other option is if water acts as the base rather than the acid. Now, which one is it going to be? Well, it depends on the collision, because there are going to be collisions. And sometimes water will act as the acid, sometimes water will act as the base. It just depends on the collision. That's it. And so we try both of these out. And so there are two possibilities here, AB and 1, 2. And so we pursue those and see what happens. When we pursue 1, 2, do you know what happens? It kind of dead ends. We could go there, but it kind of dead ends and doesn't really go beyond a certain point. However, if we produce AB, then it works. There's some kind of reaction here that we're going to see a successful reaction. And so normally you just try them both and see where you end up. And so if we did this hydrogen would go there and will form hydroxide. And then we can't really go much farther than that there. So it's not very fruitful. And so what we'll do now is, oh, actually, we don't even have time. We out of time?
4 to 3 minutes,
How many?
like 3 to 4 minutes.
3 to 4 minutes left?
We end up 4 or 3:55.
2:30 to 3:55. We end at 3:55.
I thought we were at 4. I'm sorry.
All right, no. I wanted the 3 minutes, then I could finish this, but it's all right. We'll finish this. We're going to finish AB out tomorrow.